Okay, so today's notes are on, or lesson 2 notes are on quadratic functions and their transformations. It's section 4.1, but it's our second lesson for this unit. Our objective is going to be to identify and graph quadratic functions, and the language objective is to use the correct terminology to describe a quadratic function and its features. So I want to start by talking about what a quadratic graph actually looks like. So we spent a lot of time working with their equations with factoring, but now I want to talk about what their graph looks like, because it's going to tie into what we're doing today. So the quadratic function graph is a parabola. That's the shape of the graph. It is a U shape. So a parabola is a U shape. And our quadratic functions, we're going to start by looking at our parent function, if you remember that from Unit 2, because it's the simplest version of the graph. It's y equals x squared. So our quadratic function graphs, it's a parabola or a U shape, and our parent function that we're going to look at right now is the equation y equals x squared. So I'm going to do a rough sketch. Bear with me. Here's our x-axis, our y-axis, and our parabola is, like I said, a U shape, and our parent function has a vertex here. So we have our U shape, and its minimum, since it's the simplest form of this graph, of this function, is at our vertex, or at 0, 0. So vertex, it's the same idea as the vertex from our absolute value graphs. It's the maximum or minimum of our graph. So in this case, instead of a V shape like the absolute value, we have a U shape for a quadratic. It's a parabola. But our vertex will still be at 0, 0 to start. Similarly, our axis of symmetry is going to be along our y-axis for our parent function. So it'll be at x equals 0. So again, since it's a U shape, it's going to be symmetrical across an axis of symmetry, and in this case, our axis of symmetry is x equals 0, since it's the simplest version, our parent function. And the last thing I want to do is make a table of some of the simpler values in our graph, so that when we talk about stretches and compressions, which we're going to get into again today, if you haven't picked up on this by reviewing parent functions, I want to go over some of our key coordinate points so that when we start stretching and compressing it, we can see what's happening. So we're just going to go from -2 to 2 with a table. So if I plug in -2 to my equation, -2 squared is +4, -1 squared is +1, 0 squared is 0, which makes sense since our vertex is at 0, 0, 1 squared is 1, and 2 squared is 4 again. So again, you can see it's going to be symmetrical, go down to our vertex, then back up. But these are some key points that we'll refer back to later. So I wanted to show us this graph first so that we understand that we're going to start transforming it. But backing up to tie this into what we've been doing, we've previously have worked with standard form of a quadratic. So this is one way that you can write a quadratic. This is one way that you can write the equation of a quadratic, and it's, as you may remember, f of x or y is equal to ax squared plus bx plus c. So we've worked with standard form a bit. We've ended up factoring it, which brings us to another form that we've talked about, though indirectly, factored form of a quadratic. So factored form of a quadratic is going to be f of x equals a times x minus p times x minus q. And the thing here to note is p and q are the x-intercepts. So p and q here, just that's a q if you didn't see it, are x-intercepts in factored form. We're going to spend more time on standard form later and talk about how we can get our information about our graph from that. But the one we're going to focus on today, so of our 3 ways to represent, or 3 different forms of a quadratic equation, we are today going to focus on vertex form. So I'm going to put a star here because this is what we're focusing on today, because it shows us the transformations that we're making to our parent function. So we're focusing on vertex form today because it is the way we show our transformations to our parent function. And the way we write those equations is going to be f of x equals a times x minus h squared plus k. So this might remind you of the transformations with absolute value functions where our vertex is h and k, and similarly that will be the case for our quadratics as well. So tying this into what we've done previously, in this problem, I'm going to put an arrow for each variable we're going to talk about. We have A, we have H, and we have K. So the thing here to note is A is equal to our stretch or compression. So it tells us our steepness. So similar to slope, it tells us our steepness for our graph, but our stretch or compression tells us, or A value tells us the stretch or compression, which is the steepness. H is going to tell us the horizontal translation, which is also the x value of the vertex. So x also the x value of the vertex. Sorry, that's written really small, but H is our horizontal translation, which is also the x value of the vertex. K, along those same lines, will be our vertical translation, which means it'll be the y value of the vertex. So you can say H comma K will be our vertex. So it's the same ideas that we talked about with absolute value transformations. H is how much we're moving left or right. It tells us the x value of the vertex. K, it tells us how much we move up or down on our graph, which is our y value of our vertex. And A tells us our steepness of our graph, or how quickly our U shape goes up or down, or how slowly, depending if it's getting a compression, so it would get wider and flatter, or a stretch, which would make it narrower and thinner. All right, so this is the overview of what we're doing, but I'm gonna see if you guys can recall what we did with absolute value and apply it to now quadratic graphs. So I'm gonna flip the page and do a quick check. I'll go over all of them after, but I want you to try to graph them on your own, given that we've practiced this with absolute value, and it's the same idea just being applied to a quadratic, which is a U shape rather than a V shape. So I'm gonna flip the page. So the quick checks I want you to find, I'm gonna give you a few of them. So the first one, or what I'm asking you to do is to graph the following. So the first one I have for you is f of x equals x squared minus 5. The second one is going to be f of x equals x minus 4 in parentheses, that whole quantity squared. So based on what we just talked about, try graphing these on your own. Pause it if you need to. I'm going to go over it now. So for this one, since it's not inside the parentheses, it's outside, I know it's a horizontal, and based on the information about k, I know it's going to be the y value of my vertex, so my vertex needs to go down 5. My h value is not present, so which means it's 0, so I'm not moving it horizontally, and there's no stretch, so all I'm doing is taking my parent function and moving it down 5. So I'll put my x-axis up here. So I have my y-axis, my x-axis, 1, 2, 3, 4, 5. I guess I gave myself some extra space. Actually, I'll do 1, 2. I'll move it down here. So this will be the y. This will be 5. So 1, 2, 3, 4, 5. Negatives for all of them. Just put little dashes. So my vertex is going to be here. If I follow my points, I know for my stretches, I know it's going to be the same as it was previously. So the first one was just 1, 1, so I moved up 1 over 1. And it's symmetrical, so I know it's going to be the same on either side. The next one went up to 4, so I go up 1, 2, 3, 4, and over 2, 4, and over 2. And there are the points I need to plot to draw my graph. And there it is. So for those of you that are not sure how I got these points, if I look back at my table here, I know from 0 to between the first x coordinates, I went up 1 for y. So I went up 1 for y in both these directions. So I did the same here. When I moved 1 over in the x direction, I moved 1 over in the y direction. For those first 2 points, I know it's symmetrical, so I do the same on either side. Then for the next one, I know I went from 0 to 4 when I went 2 in the x direction. So I went over 2 and then up 4, which brought me to these points. And again, they're symmetrical, so I did the same on either side. We'll have some more practice with that as we go along, but I just wanted to give you a quick overview of that. So the next one is going to be x minus 4 squared. So this one is horizontal, but no vertical. So there's only something in the parentheses, which means I'm moving it 4. But since it's horizontal, I'm doing the opposite. So I'm moving it positive 4 in the x direction. So instead of being at 0, 0, I'm moving it 4 this way. So I'm going to draw my axis over here and here. So I have my x-axis, my y-axis. I'm going 1, 2, 3, 4, 1, 2, 3. So I'm giving myself some extra space, but I know that that's my 4 for my vertex, and my vertex will be at 4, 0 since there's no vertical translation. And then my slope is going to stay the same. So as I go 1 to the left and right, I go up 1, and then as I go 2 to the left and right, I go up 4 since there's no stretch or compression. It's going to be the same on either side, and then I can draw my graph through my points. So there's my next quadratic graph, and we're all set. If it's helpful for the symmetrical part, you can draw your axis of symmetry and then count the same on either side. So once you plot this, you count over 1 from here, you count 2 over, 2 over. The next ones I want us to try, I'm going to have you do another couple of quick checks. I want you to do f of x is equal to 2x squared, and f of x is equal to negative x squared. So go ahead, try those ones on your own now. I'm going to go over them, so pause it if you need to. So now I'm not worrying about translations, I'm only doing stretches. And in this case, if you forgot this transformation, it's a reflection. So if you have a negative value, it means you're reflecting it or you're flipping it over. And since it's not in the parentheses, you're flipping it over the x-axis. It's a vertical translation, so you're flipping it down. But we'll go over these each separately. So for number 3, there's a stretch. All this means is I'm doubling all my y values I previously had. So my vertex didn't change. So if I draw my graph, 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, so I start at 0, 0. Now as I go over 1, I previously would go over 1, up 1, and plot my point here. But since I'm doubling it, I'm multiplying by 2, I'm going to go over 1, up 2. And then I know symmetry tells me I'm going to go the same amount on the other side. So I go over 1, up 2. The next one, I normally go over 2 and then up 4. But as we know, we're doubling our values. So instead of going up 4, I'm going to go up 8. So I go 1, 6, 5, 6, 7, 8. And I'm plotting that point. Symmetry tells me if I go over 2 on this side, it should be my symmetrical point. I can draw my graph, and I'm all done. The next one is going to be the negative x. So I'm reflecting it over the y-axis, and I'm going to have it opening downwards instead of upwards. So the negative sign tells you the concavity of the graph. So it's going to open downwards instead of upwards. So my vertex is still at 0, 0. My steepness will remain the same. The only thing that's changing is that I'm going to be opening it downwards. So I'm going to go over 1, down 1, symmetrical, so same on the other side, and then 2 and 4, 2 and 4. So now my graph will end up looking something like this. So that's my graph when I have a negative x. So if it's a negative in front, it opens downwards instead of upwards. We will practice some more combining these in class, but I wanted you to get a quick overview of what this looks like. We'll also try writing the equation from the graph in class, but I hope this has given you a sufficient introduction and we can practice some more together. Then make sure you write down questions, comments, concerns so we can go over them together.